Welcome to ATMOS 5000, day 41. Objectives are being pulled from Chapter 12, sections 12.6, 12.8, and 12.9. And this is the last lecture in the series for this class for now. We'll talk about the net effective fronts, and then we'll talk about the structure of some additional fronts, the occluded front, the upper level front, and the dry line. So recall that the amount of radiation that is emitted is a function of the temperature of a certain region. So the tropics are warmer than the poleward regions, and so they emit more radiation to space than the poleward regions. But the amount of radiation that we receive from the sun is unequally distributed along with latitude. In part, the radiance of the sunlight depends upon the cosine of the latitude. So you receive a lot more sunlight in the tropics than you do in the poleward regions. So as it turns out, the amount of energy that is absorbed by this atmosphere, the amount of energy absorbed from the sun, is actually greater in the tropics than what is being emitted. And in the poleward regions, beyond about 37 degrees north and 37 degrees south, the amount of sunlight that is absorbed is less than what is being emitted. So how is that possible? Well, the only way that that is possible is for heat transfer from the tropical regions to the poleward regions. And it's the atmospheric transport and the atmospheric weather that actually transports that energy from the tropics towards the poles. And so one way to think about fronts and weather in general is that it's trying to basically move cold air towards the equator and warm air towards the poles. So here we have a whole bunch of weather fronts that are located on this map, and each one of these mid-latitude weather systems associated with these low pressure zones are moving cold air from the north to the south and warm air from the south to the north. So we've already talked about cold fronts, warm fronts, and stationary fronts, and now we're going to start looking at an occluded front, which is actually quite a bit more complex. So here we have a time series of a frontal system. So at the top panel we have a cold front and a warm front that are connected near the center of the low pressure zone. And as it turns out, the cold air often is advancing faster than the warm air, and it will undercut the warm front at the surface and leaving behind an occluded front between the junction of the cold front, the warm front, and that would lead back to the center of the low pressure zone. And over time, that cold front can continue undercutting the warm front and leaving a larger and larger occluded zone. So here we have a low pressure where we have the cold front and the warm front are meeting at the junction of the center of the low pressure zone. So this is early on in the evolution of one of these mid-latitude synoptic systems. This extratropical cyclone is what we refer to these storms as. And then as we move forward in time, the cold front, the cold air is wrapping around the low, and the warm front is moving northward, but not as fast as the cold air is wrapping around the low. So here the cold front has continued to advance faster than the warm front and has actually undercut the warm front at the surface, creating an occluded zone that extends back towards the center of the low pressure. And you might notice that there are three lines here, UV, WX, and YZ, and each of these are cross sections. And what we're going to do is we're going to look at what the structure of this frontal system is at each of these cross section locations. So we're going to start off before the occlusion happens, right when the occlusion happens, and then during the occlusion. So here we go. We are prior to the occlusion. We have a cross section across this case from A to B, similar to what we had on the other one. We have cold air that's advancing. we have a warm front that's advancing, and at the surface they're distinct and have not caught up to one another yet. So right at the occlusion point, we have the cold air is now meeting the warm front at the surface, and so it is now pushing that warm air that was in that sector between the cold front and the warm front is now located up above the cool air and the cold air. And as that occlusion gets deeper, the surface front, the surface warm front, has now been lifted off of the ground as the cold front has moved underneath of it. And that warm air is now completely separate from the surface. And we have this warm air that is above the cold air and above the cool air. And this is a deep occluded system. So here we have the typical weather associated with occluded fronts. The winds prior to the passage are typically from the southeast or the south and moving to the west to northwest after the passage. There are actually two types of occlusions, a cold type and a warm type. The type that I was describing here was a cold type occlusion. In that situation, you'll have cool or cold air before the passage, and then the air will be colder after the passage of the occluded front. Pressure is typically falling before the front passes, reaches its low point during passage, and then rises thereafter. In terms of clouds, you're going to have the warm front type clouds before the passage. So that's your cirrus, your cirrostratus, your altostratus, and your nimbostratus. And while it's passing, you'll typically have nimbostratus. But if the atmosphere happens to be particularly unstable, you could end up with towering cumulus or cumulonimbus clouds. And then after the passage of the occluded front, you'll still be back into nimbostratus, altostratus, or cumulus clouds. In terms of precipitation, you'll often have light, moderate, or heavy precipitation before the passage. You'll continue to have that while it's passing, sometimes turning into showers. And in general, this entire occlusion period is a period of light to moderate precipitation. The dew point temperature will typically drop after the occluded front passes as you move into the colder air. The next type of front that we're talking about is a dry line, and a dry line is basically a differing dew point temperature. Two air masses could have the exact same temperature and have different amounts of moisture, and they would be two different air masses. For example, you could have a maritime tropical air mass and a continental tropical air mass. They could be the same temperature, but one is moist and one is dry, and so there's still two different air masses, and when one moves, you end up with a frontal boundary between those two. And so these dry lines are usually transporting drier air from the interior of a continent towards the maritime air masses along the edge. So in the United States, this often happens just to the east of the Rocky Mountains, where we have continental tropical air mass that was located over Colorado, New Mexico, or Mexico itself. And then we have a cold front that is moving down from Canada along the eastern edge of the Rockies, and we have our maritime tropical air mass that is moving up from the Gulf. And in this particular image, we have the dry line denoted by the brown dashed line. And if you look at the station models, just in the maritime tropical air mass to the east of the dry line, the temperatures are in the 70s and the dew points are in the 60s. And behind the dry line, the temperatures are still in the 70s, but the dew points are in the 30s. So it's clearly a very dry air mass compared to the maritime tropical air mass. And here we have the evolution of a frontal boundary. So we're starting off here with a stationary front where we have cold air on one side and warm air on the other. And we happen to have air that is blowing in opposite directions on either side of the front, so that the front is not advancing. And if we happen to have some divergence aloft, we can get some rising motion, and we'll start to get air that moves in towards that area of rising motion, and we'll start to get some rotation. And as it starts to rotate, the warm sector will start to move northward, and the cold sector will start to move southward. And you continue that divergence aloft, which creates the low pressure at the surface, and then you have well-defined fronts now. The stationary front has turned into a moving cold front to the south and a moving warm front to the north. As that cold air continues to advance, it can dive underneath the warm front and can create an occluded zone, or in this case, a stationary front. And here we have a stationary front or an occluded front between the junction of the warm front and the cold front and the low pressure center. So, lastly, we're looking at an upper level front. So upper level fronts by definition do not reach down to the surface. And a lot of times this happens to the east of the Rocky Mountains, where we have an air mass that was moving over the Rockies, and as it moves across the Rockies, the surface falls away, leaving a different air mass aloft. That's one way that we can get a upper level front, but it's not the only way that we can get an upper level front. Another way to get an upper level front is associated with air that's moving around the jet stream. So recall that the jet core is actually the strongest winds in the jet stream, typically happens right at the tropopause boundary. And as it turns out, there's actually a circulation that occurs around the jet core, and it is one of the places where you can actually have air from the stratosphere that is dragged down into the troposphere. And here you have a front between the troposphere and the stratosphere. And that stratospheric air, of course, is going to be warmer than the tropospheric air, and it's also going to have higher ozone concentrations. So here you can see the circulation pattern that is occurring around the jet core. That would bring that stratospheric air into the troposphere. This is often very common as these jet streams are moving over mountainous regions, and you'll end up with the stratospheric air intrusions where you have high ozone air that is brought down into the troposphere, and that is the best tracer of these stratospheric air intrusions that we have in the troposphere is the high ozone concentrations in an otherwise rural area where you wouldn't expect urban ozone to be located.